Before we start, there are some things you should know. First and foremost, this is an introductory course on the C++ programming language, so you may or may not have experience programming. Although you may learn a lot from this course if this is your first time programming, some programming experience in any programming language may be useful. Although you don't need an IDE to run your C++ code, I'll use Visual Studio Community. But you may use your favorite development environment. Just make sure to use the C++11 standard or later. You may want to read the documentation of your development environment for this. It's usually a Google search away. And lastly, as you advance through the course, you'll need to read some parts of the C++ documentation. For this, I recommend cppreference.com, which is a free online reference for C and C++. It's actually a wiki. I occasionally contribute to it, and you should too once you get enough experience in C++. Once again, the development environment you choose will be okay as long as it supports C++. Now, if you'd like to use Visual Studio Community, you'll simply have to go to its download page. The easiest way is to search online for Visual Studio Community and follow the link from Microsoft. There you will see the download link. Be sure to read the instructions which specify the system requirements. When you run the installer, make sure to select the Visual Studio Community Edition, not the Enterprise or Professional editions. Because Visual Studio supports numerous programming languages and platforms, the installer lets you select from a number of so-called workloads, so that you only install what you need. For this course, we'll use the workload titled Desktop Development with C++. At the right, you may select the optional elements you want, but the default options are okay. After the installation is done, you may want to run Visual Studio and create a project to make sure everything's okay. So in the opening screen, click on Create a New Project, then select Console App for C++, and there you can select the project name and directory. When you're ready, click on the Create button. Next, you will see your new project with a Hello World already created for you. There are a few parts of the IDE you'll be working with in this course. First, we have the code editor, which has many nice features like syntax highlight and code completion. At the left, we have the Solution Explorer, where you can see all your files. Here's the source file we are working on right now. I like to use the Auto Hide feature of this toolbar by clicking on the Pin button. This hides the toolbar to the left so you can reopen it whenever you need to. When you're ready to test your code, you can click on the Run button that reads Local Windows Debugger. You'll see the output window at the bottom reporting how the compiler is doing. This is where you'll see any errors you need to fix to compile successfully. If everything goes well, you'll get a console window with the output of your running program. You may also enter text in this window, and when your program is done, you will see the message Press any key to close this window. Now, if you accidentally move a window to an awkward location or lose one, don't panic. You can always reset to the default layout by going to the Window menu and selecting Reset Window Layout. Finally, let me show you what you should do if you get a compiling error. When you get an error message, it doesn't mean that the compiler failed because the computer made a mistake. It means that there's some error in the code you provided. So it's very important to read the information in the error message. Let me show you what I mean. Let's add a letter M at the end of line 8 to get a syntax error when I try to build. You may get this dialog asking if you want to run the last successful build. I recommend that you select Not to show this dialog again and click on No. Now the output window will show the error messages as they come up, but you may want to click on the error icon to see the error messages in a more meaningful way. This will bring up the error list where you can read each of the error messages. If you have experience debugging, you'll know that most errors are related, and fixing the first one will probably solve many others. Great, we are good to go. C++ is not just an extension of the C programming language. There are actually several differences between the two languages, and we can't assure that one completely contains the other. The main addition of C++ is that it's an object-oriented programming language. So let's briefly go through some basic elements of object-oriented programming. First, we have modeling. A model is a representation of something in reality. Modeling is a crucial concept in object-oriented programming. We may model anything, a cow, a car, a person, you name it. Now the tricky part is choosing which elements to include in your models. For example, let's suppose we want to model a car. We might include variables to represent every aspect of a car we could think of, like make, model, weight, owner, color, age, and so on. You may agree with me that there are countless aspects we could add to our model, so we may never finish our model of a car. Thus, the challenge of modeling is to figure out which features are enough to simplify our representation without oversimplifying it by leaving important details out. For a car salesperson, the car represents, among other things, its price, make, model, number of seats, and some performance metrics. For a passenger taking a hired ride, the car may represent a means for getting from point A to point B with a capacity to carry the passengers and their things. For a parking lot owner, the car may be simply represented by its size. Another important element of object-oriented programming is encapsulation. Simply put, encapsulation means keeping data and operations within their models. Well-defined models must only include information about themselves. Model operations must be concise. If a function is supposed to do A and B, it shouldn't do anything else. For example, the model of a car should not include the cost of filling its gas tank. That's more an element of the gas station model. Next, we have classes, which are the C++ construct for models. Classes contain members of two types, data and functions. For example, our car class may have a data member for the make or brand of the car, and a member function to change the paint color of the car. By the way, an instance of a class is known as an object. That is to say, if we have three variables of the car class, it is said that we have three car objects. Among other attributes, class members may be public or private. Public members are accessible by any part of the code, that is, by code outside the class. Private members, on the other hand, are only accessible within the class. But wait, there's a third access specifier. Protected members can be accessed in inherited classes. Which leads us to the concepts of inheritance and polymorphism. A class may have subclasses based on it. A subclass may inherit members from their superclass. For example, the animal class may have a data member for the number of legs, which is inherited by the dog subclass. Some subclass may add other members. For example, the bird class may add a member for wings. And there's an interesting feature related to inheritance called polymorphism, where the superclass may define some function, but the inherited version of this function is implemented differently among the subclasses, making these sibling classes polymorphic. You may be familiar with these elements from other languages like Java or Python, and I'm happy to report that C++ implements all of this and more. Although we already saw a hello world when we tested Visual Studio, I want to show you the syntax and structure of the code. One of the most important details of C and C++ is that they are case sensitive, so keep an eye out for the exact spelling of keywords and names. So, a hello world is the traditional simple program that prints out a message to the screen. It usually takes a few lines of code. In the first line, we include the libraries we'll use. This line is a preprocessor directive, which we'll talk about later. Notice that we're using a library called IOStream, which is a part of the C++ standard library, and contains objects and functions to print text to the screen and receive text from the keyboard. Preprocessor directives do not end with a semicolon. Next, we have the main entry point of your program, which is a function that is executed by default. We'll get to the syntax of functions later, but for now let me tell you that the main function must return an integer, denoted by the int keyword. Then comes the name of the function. Remember, this is case sensitive, so I'll type all lowercase main. And finally, we have the parameter list. The main function may receive either nothing or a set of strings that come from the command line, just the way you run commands with arguments in the Windows, macOS, or Linux command lines. For our hello world, we'll use an empty list of parameters. And this list is enclosed by parentheses. Now, the body of a function is a block of code, and blocks are delimited by curly brackets symbolizing the beginning and the end of the block. Now you have to decide how you prefer to place your curly brackets. I personally prefer to open blocks at the end of the control statement and close in a dedicated line indented at the same level as the opening line, like this. This is a very popular style, and you'll see it throughout the course, but you're free to use whichever you prefer. You may want to Google indentation styles for this. Another important detail is that C++ code, like most programming languages, would very soon become virtually unreadable by a human if you don't properly indent your code. Most development environments have a feature to help you with this, but you must get used to indenting your code so that any new block of code is indented a fixed number of spaces or a single tab to the right. Keep in mind that C++ compilers do not require you to indent your code, unlike Python, which enforces indentation. The first line of code will be where we print out our message. We'll do this by using an object from the IOStream file, which is a member of the standard library. This membership is represented by the scope resolution operator, : The object is called cout for character output. This represents the output window, and we must send some text to it. We do that with the left-bound insertion operator, or double characters. To the right of it, we enter whatever we want to send to the object at the left, and we may use the operator consecutively like this. The message will be "Hi there," and after it I'll send a new line character which is available by another standard library symbol, endl. We finish almost every line of code with a semicolon, but there are exceptions. For example, the lines that end in a closing curly bracket. Finally, since main is a function that returns an integer, we'll return 0 with the return keyword. You may use parentheses for the return value or not. I always do. The reason I return 0 is because 0 is traditionally used to mean that no errors came up in the program. Other values usually represent error codes, which you are expected to detail in your documentation. That's it for the hello world. Let's see it running. And there's the "Hi there" message as expected. Now let me show you a trick I'll use throughout the course to simplify my typing. Since cout and endl are members of what is known as the std namespace, you may write a line to use this namespace by default. Let me write it above the main header. Using namespace std. This allows you to stop specifying std : for every member of std. You may think of this trick as the training wheels on a bicycle for children. Once you grow comfortable with C++, you may decide to stop using this line of code. Using this line is often considered a bad practice because there are some hazards to it. so you may want to Google it and decide for yourself whether you want to use this technique or not. So at this point, I may remove the std:" specification and simply work with cout and endl. It's time to do some console interaction. In this challenge, your task is simple. Ask the name of the user and say something back. Do this by printing a message addressing the user's name. For this, you'll need to use the standard libraries cin and cout objects. Let me show you how to use cin. For this example, we'll use something similar to our hello world. Since we are going to get a string from the user, we'll need to include the string header file from the standard library as shown in line 6. Next, in line 11, I have declared a string variable named str, which I'll use to hold the user input. In the next line, we have the cin object, which is used in the opposite direction as cout. So we type cin, then use the right-bound insertion operator pointing to the target string variable. After running this line, the user input will be in str. Finally, I added a line to print out str. So let's see it running. At this point, I'm expected to enter some text, so let me type in my name. After I hit enter, we'll see my name printed back once more. Now be warned that cin only works for single words. If you want to use it for strings that contain spaces, you'll have to use a special function. Feel free to work on this project to create your solution if you want. Remember, you have to print a message requesting the user's name, then print a message using that name. If you've got your development environment correctly set up, this shouldn't take you more than 10 minutes. When you are done, take a look at my solution in the next video. Here's my solution. In line 11, we have the string variable declaration. Next, we have a cout line to print the message asking for your name. Next, we capture the user input into str in line 13. Remember, this only works for single words. And finally, the response message is composed by a sequence of insertion operations to cout. First, we have the string nice to meet you, then we send str, then an exclamation sign, and finally the end line character. This sequence works as a concatenation of all the elements involved. Let's see it running. Here's the prompt message. I'll type in my name. And there's the response. Great, let's learn some more about C++. As with any programming language, it's essential to know the supported data types. C++ supports a very basic set of data types. Let's start with integers. Integer numbers may be signed or unsigned. There are several integer types in C++. There's the int type with a bit length that's implementation dependent. Usually it's 32 bits, but it's sometimes 16 bits. We also have the char type, which is short for character. It's 8 bits wide, and it was designed to represent ASCII characters, but it's just a byte. You may use it as an integer if you want. Because these types may vary in lengths and sign, a very useful C library called stdint.h contains portable data types that specify the length and sign support of their types. For example, uint32t is an unsigned 32-bit integer, and int8t is a signed 8-bit integer. C++ also supports floating-point numbers. Floating-point numbers represent real numbers, as opposed to integers. I'm talking about numbers like pi, or 1.333, 0.5, or minus 12.44. These types implement the IEEE 754 binary floating point standard. There are three floating point types in C++: float, double, and long double. The difference between float and double is that double has a much larger range and precision than float. However, it's way more computationally expensive to work with doubles than floats. Unlike C, C++ supports a Boolean type to represent true and false. The keyword for this type is lowercase bool. In the language, the lowercase true and false keyword are defined, so you may assign either of these to a bool variable. Also in the language, anything other than 0 means true, and 0 means false. Next, we have the string class. Now, strings are not natively supported by the language. As in C, you may work with strings as arrays of characters terminated with the value 0. However, strings are supported in the C++ standard library as a class. The string header file provides the string class and lots of string manipulation functions. Lastly, we cannot talk about C or C++ without talking about pointers. This is a special data type for memory addresses. Pointers may act as references to existing variables. And the same pointer may be used to access many different variables sequentially. Now, this hasn't been an exhaustive description by any means, so I recommend that you visit cppreference.com for a detailed description of the supported types. Go to the Language section and click on Basic Concepts. Once in there, go to the Basic Concepts tab and click on Fundamental Types. Alternatively, you may simply Google CPP reference fundamental types. You'll see that there are numerous variants of each type and that most of them are implementation dependent. Take a minute or two to skim through this page. There are a handful of important aspects about variables in C++. Variables are temporary data storage units. They must be declared prior to being used. The declaration of a variable must specify a type and a name. And declarations may contain initializations. In your code, you'll have to assign values to your variables. So let me briefly show you the syntax for some of the most popular types. Integers are entered as numbers with a special format for the radix. The default is decimal, like 123 or -5. A leading 0 means octal, like 0 to 3, so be careful with this. For hexadecimal, start with 0x, like 0x3a, and for binary, start with 0b, as in 0b1100. You may specify unsigned with a trailing upper or lowercase u, as in 23u. Floats are entered with the decimal point and at least one digit to the right, even if the value happens to be an integer, and you must specify the float type with a trailing f, as in 23.0f or 0.0f. Doubles are the default floating point type, so you write the number like a float literal without the trailing f. Chars may be entered as integers as long as they fit in 8 bits, but their ASCII character interpretation is entered between single quotes. Here we have lowercase a, uppercase x, and two special characters that use the \escape character. These are the null character to delimit the end of a string and the new line character. Finally, you've already seen string literals between double quotes. Let me show you an example of variable declaration and usage for several types. I'll start with the Hello World code we wrote earlier. Variable declarations must include the type and name of the variable, and they may include an initialization. Let me declare two integer variables, a and b, and let me initialize b to 5. Notice that you may declare several variables in one line separated by commas. Notice that these two variables are at the same level of indentation as the main function. This means that a and b are global variables. Global variables are accessible to all parts of the code. Because of this, the memory for global variables is managed statically by the compiler, so they are allocated in the data segment of memory. Once the program ends, their memory is freed. On the other hand, variables may be local to their scope. By that, I mean that you may declare variables inside functions or inside loops. These variables are accessible in their scope and in scopes inside of it. Once code execution leaves a scope, its variables are deleted and the memory is freed. These are called automatic variables because they are managed by the compiler, and they are usually allocated in the stack segment of memory, which is temporary. So let me declare a local Boolean variable in the main function. Let's call it myFlag. Variable names have rules, and you should read about these rules. Again, I recommend cppreference.com for this. To make a long story short, variable names must start with a non-number character and may contain letters, numbers, and some symbols like hyphens and underscores. Also, variable names cannot be the same as any keyword in the language, like int or return. This is a good time to show you how comments are entered. A double slash comments everything to the right, so these are useful for one-line comments. The limited comments are useful for multi-line comments. These are enclosed by /* and */. Now let's use those variables. In the main function, let me assign a value of 7 to a. Notice that the assignment operator works from right to left. I'll assign false to the flag. Now let me modify the cout line to show the values of a, b, and the flag. So let's try it. There you go. A equals 7, b equals 5, and the flag equals 0, because 0 is false in C++. Now let me add some code to toggle the flag and print out three things: the value of the flag, a plus b, and b minus a. And let's see it working. And there we have the results again. The flag is 1, which is a valid true value in C++, a plus b is 12, and b minus a is minus 2. Finally, let me show you what happens when we use an unsigned variable to store a negative number. Let me add a third integer declaration. This one will be an unsigned int called positive. Making declarations anywhere in the code and not just at the beginning of a scope is a nice feature of C++, which hasn't always been supported in the history of C. Now let me add the same subtraction to this new variable and print out its value. Let's see it running. Now we get that b minus a unsigned equals, look at that number. If you use your calculator, you'll see that this number is 2 raised to the 32nd power minus 2. And this is the 2's complement representation of minus 2 in binary. The binary number is the same, but the interpretation is different. That's why you have to be very careful when deciding whether you want to use signed or unsigned integers. Now let's talk about three important components of C++ code. Let's start with expressions. An expression is a symbolic representation of a calculation, like the expressions you see in algebra. An expression may contain variables, constants, and operators. And every expression must produce a value. An assignment is a line of code that assigns a value to a variable. It must contain a left-hand side and a right-hand side expression. The left-hand side expression must be able to hold a value. And the data types of both expressions must match. This last point is not enforced by the compiler, as you saw when we assigned a negative number to an unsigned variable. So you, as a programmer, are responsible of keeping your code consistent. Lastly, let's review some of the most important operations in C++. We have arithmetic operators, plus for addition, minus for subtraction, asterisk for multiplication, / for integer division, that's quotient, and the percentage symbol for the modulo or remainder of a division. The / operator is also for floating point divisions. It all depends on the operands you use. We also have bitwise Boolean operations, that is, binary operations performed bit by bit between the operands. We have single ampersand for bitwise AND, single vertical bar for bitwise OR, tilde for bitwise NOT, and caret for bitwise XOR. Again, these are bitwise operations, not logical. Now, logical operators are the ones you probably want to use in an if statement's condition. These evaluate two operands that can either be true or false in the same logic we've seen so far. Remember, 0 means false and anything else means true. The logical operators are double ampersand for AND, double vertical bar for OR, and exclamation sign for NOT. We have relational operators to compare values, double equal sign for equality. Be careful with this one. A common mistake is to use the single equal sign in a conditional, and the problem is that this is valid because it returns the assigned value. So once again, be careful. Next we have exclamation sign equal for not equal, greater than, less than, greater or equal, and less or equal. And finally, we have three popular pointer operations. Prefix asterisk for indirection, which dereferences the pointer to its right, which is its only operand. That is to say, it gives you access to the variable the pointer is pointing to. This is not the multiplication operator despite sharing the same character. We also have prefix ampersand for the address of operator, which returns the address of the variable at its right, which is its only operand. And we have the arrow operator, which gives you access to members of classes or structures from a pointer. You may have noticed the lack of a logical XOR operator, and that's an interesting exercise to think about. Here's a hint. What does the not equal relational operator do? Since you'll be seeing a lot of expressions, assignments, and operations up ahead, you may want to consult cppreference.com to learn more. Just Google CPP reference operator precedence, and you'll see an exhaustive list of operators and their precedence. Take a minute to browse through it. In the C++11 standard, the language got a very nice addition called type inference. It's a convenient way of creating a variable with the type that suits the value you want to assign to it. The only catch is that you must initialize the variable at declaration. Let me show you how it's done. I'll declare 6 variables of automatic type named A, B, C, D, E, and F, and initialize them with different types. The placeholder for the type is the auto keyword. So A will get a small integer, let's say 8. Now B will get a very large integer, one that exceeds 32 bits. An 11-digit number will do the trick. C will get a floating point number, say 3.14, with a trailing lowercase f. That's the constant specifier for floats. D will also get 3.14 without the trailing F. Floating point constants are doubles by default. E will get the Boolean constant true, which is 1, but I'm using the constant true because it is defined in the bool type. And finally, F gets a single character D. In the main function, I'll print out the type of each variable in a separate line. To do this, we'll use the type ID operator from the typeinfo header file in the standard library. It receives a variable and returns its type. Now the name of this type is accessed by the nameMember function. So let's see it running. As you can see, we have the expected types: int, int64, float, double, bool, and char. Please bear with me on this exercise. The type ID operator is implementation dependent, so it may work differently for you. Some implementations show a single character to represent a type. So don't worry if you get different results or even an error. I simply wanted you to see how the auto keyword performs type inference. C++ is a compiled language, so the code goes through a pipeline of software tools which extract the semantic elements written by the programmer. One of the first steps your code goes through is the preprocessor, which is not related to the microprocessor. There are several directives addressed to the preprocessor which contain information about what to add or remove in the code. The compiler will receive a somewhat modified, or rather preprocessed version of the code. These directives, like include, define, and ifdef, are useful for using libraries, defining constants, and selecting blocks of code for different compiling scenarios. So let's see some popular directives. First off, all directives start with the number or pound character and occupy one line each. There's actually one directive I've been using in all the exercise you've seen so far. That's the include directive. This one is used to insert the referenced file into your code, replacing the directive line. Yes, the whole code in that file. In line 5, we have include IOStream. Notice that IOStream does not have a path or extension. Also notice that it is enclosed in angle brackets. That means that the file will be searched in a predefined location, usually specified by the development environment, like a default include folder. So you can think of this as including known standard libraries or installed libraries. IOStream is part of the standard library, and these files usually don't require an extension like .h or .hpp. The same applies for the string header file, so let me include it. Next, I'd like to show you a header file from the C standard library I mentioned earlier. That's stdint.h. This file provides fixed-length definitions for integer types so that you don't have to depend on the implementation of primitive types like int or char. Now, this header file is from the C library, so it has C code in it. Remember, C is not C++. So some of the most popular C header files in the standard library have been made available for C++ code in their special version preceded by lowercase c. So this one is named cstdint. The second directive I want to show you is define. These directives define symbols to mean whatever you type at the right. These symbols are called macros. You should be careful if you're defining something other than a simple constant, because what this directive does is find and replace. So for example, let me define a constant called uppercase capacity, and it will mean 5,000. Some of us prefer to name our defined constants with all caps. Now, every time the preprocessor finds the symbol capacity, all caps, it will replace it with 5,000. Also notice that directives do not end with a semicolon. Now let me quickly write the contents of the main function. I'll declare two integers of different sizes. One will be a 32-bit signed integer from stdint. The format goes like this. It starts with a u if it's unsigned, this one is not, then int, then the bit length, which is 32, and lastly underscore t for type. So that's int 32t. This variable will be called large, and it will be initialized at capacity. The next one will be an unsigned 8-bit integer. I'll name it small and initialize it at 37. Now let me add them together and save the result in large. There's a shorthand operator for this, the plus equal operator. So this line is equivalent to large equals large plus small. And finally, let me print out the value of the large integer. The third type of directives I'll show you are used for conditional inclusion of code. They are if-else conditionals, and they work in conjunction with defined directives. Remember, these are directives, not the if-then statements in the programming language. Here's how they work. In the main function, let me add a line to report that we are about to perform the addition. This can be useful for debugging purposes, so I don't want this line to make it to my final implementation. So the way to include code conditionally is by using the ifdef directive, which means if defined. It includes the following block of code if a macro has been defined previously in your project. So now in line 16, I'll type ifdef debug. The block ends with the endif directive, and the block will be a line where I print the message about to perform the addition. Great, so let's see it running without the debug macro. So here we only see that the large integer is 5037. Now let's add the definition of debug. Define debug. Notice that debug doesn't need to extend to any value if it's only used for an ifdef directive. Let's try it again. Now you can see the debug message when that line was executed. So there you have it. Now you are free to choose whether to leave or comment out the debug definition line to include or exclude portions of your code. Now let me tell you a little more about constants in C++. Constants are identifiers with values that will not change during execution. They are useful as parameters in your code, for example, to set the size of a screen or the length of a memory buffer. Constants may be implemented with defined directives or as regular variables. On the one hand, we may create constants with preprocessor directives. The defined directive schedules a find and replace operation so that the code that is sent to the compiler has all the instances of the defined symbol replaced by its value. These defined symbols are known as macros. An example would be to define the number of rooms in a house as 4. Now, you should be aware that the use of define is sometimes discouraged and considered a bad practice. That's because macros don't have a context and there's no compiler enforcement for basic features like types and syntax correctness for macros. Besides, there's a better alternative. You can define regular variables as constants using the const qualifier. This is used in a regular variable declaration. Remember that declarations specify a type, so the compiler will notice any irregularities in the code related to the type. Also, scope encapsulation is enforced, so you have the order embedded in the language. Lastly, let me give you a warning. The const qualifier is not exactly the same in C and C++. The C version only means that a variable cannot change, but it lacks most of the features implemented in C++. That's one of the reasons why macros are more common in C than C++. Arrays are collections of data. Each element is accessible by an index. Elements are homogeneous, meaning that they are all of the same data type. Arrays are fixed in size, so you may not resize them. And lastly, elements are contiguous in memory. That means that the whole array is a sequential block of memory addresses. So let me show you some arrays. Let's start with an array of integers where we want to store the age of 4 people. The syntax goes like this. First we specify the type, that's int. Then comes the name of the array, age, and then between square brackets the capacity of the array. We'll use 4. Now in the main function, let me assign values to each element in the array. Now this is important. Arrays in C and C++ are indexed from 0 to n-1, where n is the capacity of the array. This is a common source of bugs for beginners, so please try to keep it in mind. To access an element for reading or writing, you simply enter the element's index between square brackets after the name, as you can see in line 12. Now let me assign the remaining elements. Once again, notice that I've indexed from 0 to 3 because indexing starts at 0. Next, let me print out the contents of the array. I won't use loops just yet, so bear with me. Alright, that should do it. Let's see it working. There you have it. The ages are 25, 20, 19, and 19, just as expected. As with scalar variables, you are allowed to initialize arrays at declaration. You do that by providing a list of values between curly brackets. So in line 10, let me define a new array of 3 temperatures in degrees Celsius. Let's use floats for this. Now notice that I will not specify a length between brackets. That's because I will assign a list with a constant length. Let's say 31.5, 32.7, and 39.8. Notice that I didn't type an F at the end of each constant, so that's actually a list of doubles. Sometimes this is okay. In this case, the compiler can safely assign the float version of those values to your array. To learn more, you can go to cppreference.com and search for implicit conversions. I'll tell you more about typecasting or type conversions later. Also notice that, although I am initializing this array at declaration, auto doesn't work for arrays, so the type needs to be specified. And now let me add print lines for this array at the end of the main function. And I'll separate the arrays with an additional end line. Let's see it working. Once again, here we have the expected values. Now let's add some constants to our code. So let's go back to the declaration of the integer array age. Here I have used a number for the length, but suppose that the length will be used several times in the code. If we'd like to change that length, refactoring the code could be tiresome. Instead, we should use a constant with a name for this. Remember, we have two options, macros and constant variables. Let's use a macro first. So let me define age length as 4. Now let me change the symbol in the array declaration to age length. Let's compile. And we have an error. So let's see it. It says that the compiler expected a closing square bracket. The reason for this error is that our constant definition had a semicolon at the end, as if it were a line of C code, but it's a preprocessor directive. You see, semicolons at the end of directives are not optional. They should not be there. So let me fix that. And let me add an extra line that uses the age length symbol for it to be useful. I'll print the length of the array before printing its contents. The age array has age length elements. Let's see it working. As you can see, the length is shown correctly. The age array has 4 elements. Now let me show you the recommended alternative to macros. First, I'll comment out the macro definition in line 9. And now I'll type const int age length equals 4. Remember, this is a C++ line of code, so it requires the equal character for the assignment and the semicolon at the end. Just as a sanity check, let me run this to confirm everything went well. Great, let's move on. Now let's talk about strings. As I mentioned earlier, strings are not a type natively supported by the language. However, C++ supports the same implementation of strings in the C programming language. In C, strings are arrays of characters, that is, a sequence of consecutive characters ending with the null character, which is 0. More importantly, the string class in the C++ standard library is a widely used model for strings with lots of useful functions. Let me show you some examples of C character strings and the string class. Partly my goal is to talk you into using the string class rather than character arrays, because, well, the string class is the intended way of handling strings in C++. I'll start in line 6, including the string header, which contains the string class. I'll also include the C string header, which contains functions to handle character array strings. Remember that the letter C at the beginning of the name means that this is part of the C standard library. Now, starting at line 11, I'll declare 2 character arrays, as in C, and 2 string objects, as in C++. The first character array will be called array_str1. It will be able to hold 25 characters, and I'll initialize it to a string. Now let me define a constant for the length above. Now I want you to see that strings are somewhat supported by the language. At least constant strings are. They are enclosed by double quotes. So let me write, "Hey guys," and leave a space at the end. This constant string means a sequence of ASCII characters terminated by 0. All 8 bits of the character after the last space are 0. The second array will be called array_str2, and this time I won't specify a length, and I'll initialize it to "What's up?" Now I'll do something very similar with 2 objects of the string class. I'll name them stdstr1 and stdstr2, and initialize them with similar messages. Now let's go to the main function and concatenate the 2 character arrays and the 2 string objects separately. I want to give you an idea on how to do this in both implementations. First, for the character arrays, the C string header file provides the strcat family of functions. Visual Studio enforces using the strcat_s version of it. You may have to use the regular strcat without the underscore s. It depends on your standard library distribution. This function takes in 3 arguments. First, the destination string, which has the first part to concatenate and will hold the resulting concatenated string. Then the maximum length to produce. I'm using length 1 or 25 because that's the size of the destination string. And finally, we specified the second array to concatenate. Now, this function modifies the first string, which is not always convenient. Let me print that out. As for the string class, I can concatenate the strings inside the printing line of code. There's a very cool feature of C++ called operator overloading. Overloading an operator means that you can redefine the operation performed by an existing operator, tapping into the semantics of the language. A nice example of this is the plus operator, which for numbers is a simple addition, but for the string class, it means concatenation. Another convenient feature of this is that none of the operands get modified. Both strings remain intact after performing the operation. This way I can simply add these 2 strings together, so to speak. Let me run this. And here you can see both messages correctly stitched together. Hey guys, what's up? And hi everybody, how's it going? That's it. I hope you find the string class convenient. You should have a very good reason to resort to character arrays in C++. That reason is usually to make your code compatible with existing C code. This hasn't been an exhaustive demonstration of the capabilities of the string class by any means. So please go to cppreference.com and check the entry on the string class for a detailed description of its functions and operators. It's time to talk about typecasting, one of the most valuable elements of C++, which gives you virtually full control of the data you're working with. Simply put, typecasting is specifying how to interpret a piece of data. It's useful for converting data types. For example, you may have a 32-bit integer which you want to convert to a floating point number. Remember that floats and integers have very different encodings. The syntax is simple. Just type between parentheses the type you want, followed by an expression which evaluates to the value to convert. Let me show you 3 examples of type conversions. The first example will have implicit conversions, that is, conversions that don't explicitly cast the values. You've seen some of these before. For this, I'll use 3 variables starting at line 10. The first one is a float named FLT for float, and I'll initialize it to -7.44. Remember, the F means that it's a float constant, not a double. The second will be a signed 32-bit integer named SGN, as in signed, and lastly an unsigned 32-bit integer named unsgn, as in unsigned. So in the main function, I'll have the same value in all 3 variables. So let me assign FLT to SGN. Since we cannot assign a floating point value to an integer variable, the type will be converted. This is an implicit type conversion or casting. When you assign a float or double to an integer, the value gets truncated, so we expect -7 here. Next, I'll assign SGN to unsgn. That is, I'm trying to assign a negative number to an unsigned variable. Since this isn't reasonable, this time the number will be copied as is. That's the 32-bit version of the 2's complement of 7. This is the same binary number, but it means different values in the variables. Let's see their values. I'll write a printing line for each, indicating their type. Let's run it. So here we have the original number for the float type, -7.44. We also get the expected value for the signed integer, -7. And for the unsigned integer, we get that big number. So if you grab your calculator and enter 2 to the 32nd power, and then subtract 7, you'll get this number. So this is the 2's complement representation of -7. However, it is stored as an unsigned number, so the most significant bit is 1, and that means a big number. Great! Now let's see a second example where I'll convert a temperature value in degrees Fahrenheit to Celsius. This time I'll use two regular int variables starting at line 22. Remember, the length of the int type is implementation dependent, but I'll stick to small numbers. Let me start by initializing the Fahrenheit variable to 100. The conversion to Celsius goes like this. Celsius equals 5/9 multiplied by the Fahrenheit value minus 32. Let's see what we get if we leave the expression like this. So let me print their values and run the code. As you can see, we get 0 degrees Celsius, so something must be wrong. The problem is that the expression 5 divided by 9 is a so-called constant expression, which the compiler takes care of. It doesn't make it to the code that will be executed by the processor. Moreover, since both operands of that division are integer constants, the operator calculates the integer division, the quotient. So the quotient of 5 divided by 9 is 0. As you can see, Visual Studio is showing just that. To get the correct conversion coefficient, we need a floating point division. We may do that by converting either of those numbers to a float or double. That's because expressions always convert the types of their values to the largest type present. So here I may explicitly cast the 5 to float, or alternatively, I could enter the constants as floats or doubles. Here I'll do both. 5 will be explicitly casted to float, and I'll rewrite the 9 as 9.0. Now let's see it working. There, 37 degrees Celsius seems more like it. Now for the third example, I'll show you how to extract the integer part and the fractional part of a floating point number. Let's use a float named weight. And let me assign 10.99 to it. And now I'll print the float value in one line, the integer part in another line, and the fractional part in a third line. So the floating point number is weight. The integer part is the truncated version of weight. We get that by casting weight to an integer type. I'll use int. Now for the fractional part, I'll need to get rid of the integer part, and then shift the decimal digits left to get an integer of as many decimal places I want to show. So, to get rid of the integer part, I can subtract the same integer part from the floating point number. This partial expression should contain 0.99. So now I'll multiply this number by a power of 10 so that the integer part of the result contains all the decimal places I want to show. Since I want 4 decimal places, I'll use 4 zeros, or 10,000. Let's see it working. There you have it. The float is 10.99, the integer part is 10, and the fractional part is 9899. Shouldn't this be 9900? Well, yes, but remember that we are using floating point numbers, which are approximations with a small error. Now, this is not a limitation of C++ or its libraries. It's a limitation of the floating point number representation. You'll get the same result if you try this in Python or Java. These are the real numbers you use in your computers and smartphones every day. You'll get a better approximation with doubles, maybe enough to show 9900 in the fractional part. So try changing the type of weight to double and see what happens. It's time for another challenge. This time your task is to perform some numeric operations to finally calculate the average in an array of 5 integers. Just add the values and divide by 5. You'll have to store your result in a float variable, so be careful with that division. To test your calculations, try using a combination of numbers where the average is not an integer. Finally, print that floating point average on the screen. Feel free to start with the code provided in the exercise files, which contains the declaration of the array and the floating point variable, and also the line to print the results. This way, you can concentrate on the calculation of this average. This challenge shouldn't take you more than 15 minutes. So have fun and watch the next video for my solution. Here's my solution. First, in line 10, I have created an array of 5 integers named nums, and I have initialized it with some numbers. Next, I declared a float named result. Next, in line 12, I didn't need to cast the elements of nums or their sum to float because I'm assigning this sum to a float anyway. Then I'm dividing the sum by 5. Notice that I'm using the shorthand operator for dividing result by 5 and updating its value. Finally, I print out the result, so let's see it working. And here we see that the average is the expected value. I hope you're getting the hang of this. There's still much to learn. Now we are going to talk about C++ structures, which are containers of heterogeneous data members. This means that you can group integers, strings, and other objects in one structure that contains them. Structures are useful for implementing simple models that only need to have data members. Structures are also available in C, and do not follow the same syntax rules in C++. Let's see a simple example of a structure. Let me start by defining the structure. For this, we will use the struct keyword followed by the name of the structure. We'll use this structure to make a simple model of a cow. So let me write this definition at line 10. The contents of the structure are enclosed by curly brackets, and the closing bracket does require a semicolon at the end. The cow structure will contain a string member for the name of the cow, an integer member for the age, and a byte integer to encode the purpose the owner of a cow will assign to her. I'll use the unsigned char type. That's it. Now, I mentioned that the purpose element is an integer that encodes the purpose of the cow. By that I mean that some defined value will represent one purpose, a second value will represent a different purpose, and so on. So for example, 0 will represent that the cow will be used for dairy or producing milk, and 1 will mean that the cow is intended for meat, and so on. Now, we could define constants for these purposes, but there's a more appropriate way of doing this, and that's an enumeration. Enumerations are sets of symbols that act as constants, and they are usually assigned consecutive values. That's why they're called enumerations. One good reason for preferring enumerations over constants is the encapsulation they provide. So let me define an enumerated type above. This starts with the enum keyword followed by the name of the type. Next, we have a list of symbols which will be assigned sequential integers starting from 0. So my purposes will be called dairy, meat, hide, and pet. Now let me show you how to use this structure. Let's go to the main function and assign values to a cow variable. Let's call it myCow. To access the members, we use the point operator. So my cow's age will be 5. Her name will be Betsy. And her purpose will be dairy. And finally, let me print out Betsy's info. Let's print the name, and notice that I'm not printing the purpose, just the encoding of it, as in Betsy is a type 3 cow, for example. And now let me print the name and age, as in Betsy is 7 years old. And there you have it. Betsy is a type 0 cow. Betsy is 5 years old. Classes are basic elements of object-oriented programming. Classes are intended for implementing models. Classes contain two types of members, data and functions. And just to be clear, classes mean the same thing in C++ as in Java or Python. So I'd like to start with the previous example where we modeled a cow with a struct. I want you to see how similar classes and structures can be. So the first thing I'll do is change the struct keyword to class. That's almost it. In fact, let's try it. We got some errors. The first one reads, member cow age is inaccessible. That's because in the main function, I'm trying to access the cow's members, but by default, class members are private. So with this error, we see that the class is actually doing its job of hiding its members from the outside world. Just for you to see how this class may behave just like the struct we had, let me add the public keyword to all members of the class. You simply type public and a colon. So there you have it. We've converted a structure into a class. Well, actually, it's more like I've forced a class to be used as a structure. Classes offer all the elements of object-oriented programming, and we should take advantage of those. So let me start by applying a feature of encapsulation, which is hiding the data from the outside world. So I'll explicitly specify all members as private instead of public. Now we have to modify our code to be able to access the age, name, and purpose of the cow, as they are now private. For this, it's important to note that there are two types of data access going on in the main function. We are writing and we are reading the data members. When we assign values, we are writing into the data members, and when we print their values, we are reading them. It is always recommended to keep your data private as often as possible, but remember that classes can have members of two types, data and functions. So a typical means of accessing the data is by defining member functions called setters and getters. Setters write into data members, and getters return their values. Now, as you may already know, functions are modules of code that perform a task. Functions may take in data and return a value. Functions can be called from your code, including other functions. So let me define three getter functions: getName, getAge, and getPurpose. And they will all be public. Functions must first specify the return type, then the name of the function, and then a list of parameters between parentheses. The first one will return a string, and it will be called getName. The body of the function is a code block, so it's encoded by curly brackets. Getters are super simple. They do not receive parameters, and they just return a data member with the return keyword. Let me write the rest of the getters. I guess I don't always use parentheses in the return expression. I'll write the setter functions later, but now we'll use a very special public member function known as the constructor. The constructor of a class is called when an object is created. An implicit constructor is always implemented, which simply creates the object, allocating memory for the data members. However, you can always write additional versions of the constructor by taking a custom set of parameters. This is known as overloading a function, and it means defining a function with the same name of an already defined function, but with a different set of parameters. A classical constructor overload receives initialization values for all the data members. That's what I'll write next, so let's go to line 14. A constructor is the only kind of function that does not specify a return type, and its name must be the same as the name of the class. So this will be cow, and the parameters will be the same members. I'll use different names for the initializers to avoid ambiguities. So I'll receive a string name I for initializer, an int hi, and an unsigned char purpose I. The body of the constructor should contain the initialization code you want for your new objects. In our case, it's simply assigning the values to the members. At first, it may appear that setters and getters are taking away the benefit we got from private access in the first place. But the purpose of having private members is not to make them unavailable to the outside, but simply to restrict their access to code within their class. If you write a class with elements that are correlated, you don't want the user to tweak the data freely, possibly breaking something. It's best to have a function written by you, the author of the class, to perform operations that affect the data. Now our class is functional. Let me update the main code replacing the member access expressions with the constructor or the getter functions. So line 35 will be modified to a call to the initializing constructor. We do that by writing the name of the new object as if it were a function call, including the arguments as a list between parentheses. This calls the constructor we just wrote. So this cow will be called Hildy, she'll be 7 years old, and I want her as a pet. Notice that this line also replaces the following 3 lines. Now for the reading access of members, I'll replace the name of the data with the name of the getter function, which is the same but with get underscore as a prefix. Don't forget the empty list of arguments. And that's it. Let's try it. Now we can see that everything went well, as Hildy is a type 3 cow and Hildy is 7 years old. Now, just for completeness, let me write just one setter function for the age in line 28. Remember, this must be public, and it will not return anything. This is specified as returning the void type. Now the setAge function will do the same as the constructor, but only modifying the age. As an exercise, go ahead and try using this setter function. Then write the remaining setters for the name and purpose of the cow. It's time to talk about source and header files. But before we do, let me show you how your source code gets compiled into an executable. A compiler toolchain is a pipeline of software tools that convert code in a few big steps. There are 3 cases of compiler input I want to show you. Now think of these 3 cases as 3 important parts of a single software development project. The first case is when you write your C++ source files. Then you feed those files to the compiler, which is the first big program the code goes through. The compiler translates your C++ code into assembly language, which is a human-readable version of the native language of the target CPU. So a new file with assembly code is created. This file is fed to a second program known as the assembler. The assembler produces an object file, which is almost executable, but it may contain just pieces of the code you want to use in your final executable. The second input case is when you write your own assembly code. Although this can be a hassle, sometimes you have no choice but to write some low-level code. This is often the case when you need to write a peripheral driver. So in this case, you may feed an assembly file to the assembler and it will produce another object file. The third case is when you include libraries for which you don't have access to the source code. In fact, libraries are often distributed as object files or some compatible variant. But you may include these just like we've been including IOStream or string in our examples. Now we're left with a handful of object files, which are correlated pieces of your project. These files are sent to a third program known as the linker. The linker's job is to stitch these object files together to produce an executable binary file. This is the program you finally get to run. Specifying all the files to compile is fairly easy if you use an integrated development environment, or IDE. However, at some point you may have to work with a compiler in the command line, and it can get complicated. All this information is orderly specified in a text file known as a makefile. Once again, IDEs take care of this for you. Now let's focus on the C++ source files. C++ code is usually written as a header and implementation file pair. These two files have the same name, but the header file usually has the .h extension, while the implementation file has the .cpp extension. Header files contain class definitions and function declarations. They may also contain macros, but no executable code. Implementation files contain, well, the implementation of all functions declared in the header file. That's the executable code. Implementation files must include their corresponding header files because the compiler needs to see the class definitions and function declarations before seeing the code in your implementation file. Your external code, the one that uses your classes, should only include the header files, not the implementation files. And lastly, all implementation files must be compiled. So let's take our cow class and take it to its own cow.h and cow.cpp files. I'll add the files in Visual Studio, but it's just as simple in pretty much every other IDE. I'll start with the CPP file. So let's go to the Solution Explorer, right-click on Source Files, and add a new item. It'll be a C++ file, and I'll name it cow.cpp. This action will include this CPP file in the list of files to be compiled. Here's our new empty file. And now for the header file, let's go back to the Solution Explorer, right-click on Header Files, and add a new item. This will be a header file, and I'll name it cow.h. Notice that the new header file starts with the directive pragma once. This is telling the compiler to only include this header file once. It's very common to include the same header file in multiple source files. And this is not necessarily a bad practice. So this pragma directive prevents an error where the compiler finds definitions it has seen before. That being said, the use of pragma once is not standard. We can see that Visual Studio supports it, but not all compilers do. So an alternative for this is using an include guard. An include guard is a simple trick using the if-and-def directive. It works like this. You start your header files with if-and-def some macro, which usually mimics the file name. This one is called cow_h. The directive means if the cow_h macro is not defined, then include the following code. We close the statement with end-if, usually with the macro name as a comment. And the first thing in the body of the conditional block is the definition of the macro. So that's define cow_h. Again, This is called an include guard, and it is supported by all compilers. I'll leave the pragma and the include guard for this file, but usually only one is used. Now let me cut and paste the class and enumeration definitions from the main source file called codedemo.cpp to cow.h. Notice in lines 10 and 15 that the string class has a red underline, indicating that it is not recognized. Let me fix that by including the string header. Also, since I haven't used the using namespace std line, I must specify the scope of string. The using keyword is considered a bad practice inside header files because header files are going to be included by external code. So adding the line using namespace std in a header file would force the whole project to use that namespace. That may cause ambiguities. So let me specify that I mean std : string now in lines 11 and 16. We're almost done. The only problem is that the header file contains the implementation of the member functions. So I'll move the implementations to the CPP file, but I'll leave the declarations of these functions. Basically, I have to leave the header of the functions ending each line with a semicolon. So first, let me copy the implementations and paste them to the CPP file. Now let me get rid of the implementations in the header file. There, our header file is looking good. Now let's tidy up cow.cpp. First, I need to include cow.h. And now I need to resolve the scope of all the members of cow in this file. It's very simple. I just have to type cow : before the name of each function. The first one is the constructor. Then we have getName, and so on and so forth. Finally, let me include cow.h in the main source file. And now let's compile and run just to make sure we didn't break anything. It's all looking good. Pointers are an essential part of the C programming language, which is the foundation of C++. In this course, we'll only cover the basics of pointers. So pointers are a special type of variables that hold memory addresses. So for example, for 32-bit architectures, pointers are 32 bits wide. Let's suppose we have this partial memory map with the locations shown at the left, and the slots are the memory units. Now the memory is organized with an address for each byte, and I'll show you an example with 32-bit integers. That's why addresses are shown in steps of 4, because each integer takes 4 bytes. So when you declare a 32-bit integer like this, int a equals 37, the compiler reserves a memory location for it. Let's say a got address 104 assigned. Since we initialize it at 37, the contents of that memory address will be 37. Now to declare a pointer, the syntax goes like this. We specify the type of the variable we will be pointing to, followed by the name of the new pointer, preceded by an asterisk. That's int *ptr. Remember that pointers are variables themselves, and so the pointer is allocated at some memory location. In this example, let's say it goes to address 120. Now it gets interesting. If we assign an address to the pointer, then it will point to that address. So let's make ptr point to A. you can do it like this. ptr equals %a. This prefix ampersand is the address of operator, and it does precisely that, return the address of the variable at its right. If we run this line of code, the contents of address 120 will be the address of A, or 104. Because of this, it is colloquially said that ptr now, quote, points to A, unquote. Let's see that example in a live demo, and then something a bit more useful for us. I'll start with the previous example because I'll use the cow class at some point. I'll start by declaring A and the pointer as we just saw in line 11. Now in the main function, let me assign the address of A to ptr. Now let me add some lines to print the memory addresses and contents of the variables. First, we'll show the content of A. For this, we simply use the variable's name, A. Now we'll show the address where ptr is pointing to. Remember, this is the content of the variable ptr. So I'll simply use the name of this variable again. Now we'll show the address of A. For this, we use the address of operator we used before. Now let me print the content of the memory address where ptr is pointing. To access this data, we use the indirection operator. That's a prefix asterisk. Notice that cout will print an integer for this last value, not a string, or a floating point number, or anything other than an int. That's because we declared ptr as a pointer to int. That's one of the reasons to specify a type for the target of a pointer. And lastly, let me print the address of ptr as a variable. Again, I'll use the address of operator. Now for the addresses, we will not see 104 and 120 as in the example. Instead, we'll see whichever addresses are assigned to the variables at runtime. Let's see these results. We have that the content of A is 37, ptr is pointing to address 00680000, the address of A is the same as where ptr is pointing, that's good. Where ptr is pointing, we have 37, that's also good. And lastly, the address of ptr is different than the address of A. Great. So this example may have shown you how pointers work, but pointing to existing variables isn't particularly useful. One of the most important applications of pointers is dynamic memory management. When you declare a variable, you are statically allocating memory for it. The compiler knows that space in memory will be needed. However, most real applications create variables and objects in memory during runtime. This is known as dynamic memory management. In C, it is common to dynamically allocate memory using the malloc family of functions, which is short for memory allocation. You, as a programmer, are responsible of freeing the memory you allocated in runtime to avoid memory leakage. But this is where C++ really shines. The use of pointers is supported by the language to dynamically allocate memory for new objects when calling the class constructor, and also to free their memory when you no longer need them. Let me modify our code for a cow by using dynamic memory allocation. So instead of declaring a cow object statically in memory, let me declare a cow pointer. I'll do that in the global context in line 13. I called it my cow. And now, in the former declaration line, line 25, I'll assign to this pointer the address of a dynamically allocated instance of the cow class. This allocation is done with the new operator. You just type new and then call the constructor of the class by its name, like this. MyCow equals new cow, and this cow will be Gertie, age 3, for hide. We are almost done. Notice the red underlines when we try to access the members of MyCow in lines 26 and 27. That's because MyCow is no longer a cow object, but a pointer to a cow object. So the dots, or member of object operators, are inappropriate. So the correct way of accessing the members of a pointed object would be to first dereference the pointer and then access a member of the object the pointer is pointing to. For example, in line 26, I could change the access of myCow.getName to *myCow. I have to enclose this in parentheses to dereference the pointer, and then .getName. So this is valid, but it requires a set of parentheses, and it can get messy if you dereference a series of pointers in structures like trees or linked lists. So there's a shorthand operator for this. It's the member of pointer operator, and I love it because it's a nice arrow. You simply place the arrow between the pointer at the left and the member at the right. No need for parentheses. Finally, remember that this object was dynamically created, so I'll delete it when I'm done using it. We do that with the delete operator, which does the opposite of the new operator. In this case, the program will end right after deleting the object, so the whole memory will be freed. But it's important to delete the objects you no longer need to avoid memory leakage. By the way, the delete operator calls a special function in your classes called the destructor, which is useful for freeing dynamically allocated memory within your objects. So let's see if this new code works as expected. And it looks like it does. Gertie is a type 2 cow. Gertie is 3 years old. References are a special category of data types I haven't yet mentioned. References are aliases to existing variables, so a reference becomes an alternative name for a variable. To declare a reference, you simply use the type you want followed by ampersand. Here we have a declaration of a reference named myRef, which makes reference to an existing integer named myInt. Once declared, references use the same syntax as the referenced variables, so you don't have to dereference as a pointer, for example. Now, it's important to point out two things about references that have certain implications. First, references are not pointers. And second, references are not objects. Moreover, references don't have an address, and this has some important implications. First, there are no arrays of references. That's because to index an element in an array, you need an address. Second, there are no pointers to references, for the same reason. And third, there are no references to references. Actually, you may initialize a reference to another reference, but they will both be aliases to the original variable, so it doesn't make much sense to declare a reference to a reference. Since pointers and references both allow us to refer to a variable indirectly, let me tell you some important differences between them. For pointers, initialization is optional, whereas references must be initialized at declaration. This means that a reference guarantees you'll find valid data when you use it. That's not the case for uninitialized pointers. Pointers can point to different objects. That is, you may use the same pointer to point to one variable, then make it point to another variable, and so on. On the other hand, references can't reference a second object. They are stuck with the object that was assigned to them at declaration. Pointers have several related concepts. For example, a pointer can be declared with the void type, which simply means that the pointer may point to an object or variable of any type. Pointers can also be assigned the null value, which means that the pointer isn't pointing at valid data. References, on the other hand, have a fixed data type and a fixed object to make reference to. Pointers may have multiple levels of indirection. By this I mean that you may access data with a pointer that points to a second pointer, which points to the data. That's two levels of indirection. Now, references have only one level of indirection. As I mentioned earlier, declaring a sequence of references simply makes multiple aliases to the same data. And lastly, pointers must be dereferenced when you want to access the data. And there's no need for dereferencing a reference because it's simply an alias, another name for a variable. So, based on these references, you may conclude that pointers are more powerful than references, but references may be safer than pointers. So far, references don't seem very useful because having another name for a variable doesn't really solve a problem. So here we have some useful applications of references. First, when you write a function, all parameters are passed by value by default. But you may also pass parameters by reference. Among other things, this means that you may modify the variable that was sent as an argument within your function. With references, you may avoid copying large objects which may contain large amounts of data. If you use a parameter by reference, the program will not end up making an unnecessary copy of that data. And the same applies to for loops. There's a special form of for loops that uses a variable to iterate through a container like an array or vector. This variable may require to copy each element in each iteration. References help us avoid this unnecessary copying of data. Although we have talked about arrays, I don't recommend using them for your applications as a first option. Instead, you should consider using STL vectors. These are dynamic size containers. That means that you may resize them in case you need to add data to your collection or delete elements. The memory required for vectors is managed for you. That means that you don't need to allocate or free that memory manually. However, if the objects you are putting inside your vectors allocate memory manually, well, you're responsible for those as usual. Vector is a generic container class. That means that vectors can be implemented for storing any type of element, ints, floats, strings, or even objects of your own classes. It also means that there are numerous member functions for manipulating vectors conveniently available within the class. Vectors are a part of the C++ standard template library. This is a special set of containers, functions, and algorithms included in the C++ standard library as part of the generic programming style. Let me show you a few examples of STL vectors with integers and the cow class. The first thing we need is the vector header. Now let me declare a vector of integers in line 12. Remember, this is a template, so we have to specify the data type. We do this with angle brackets. I'll name this vector primes. Vectors come empty by default. Let me confirm that by printing its size. Notice that I'm using the size function for this. Yes, the vector has 0 elements. Now let's add elements to it. Vectors have two ends, a front end and a back end, and we may only insert elements through the back end. The reason is because vectors are guaranteed to store elements consecutively in memory, so inserting at the front would always require reallocation. So, starting at line 15, I'll use the pushback function to enter 2, 3, 5, 7, and 11 one by one. Now let's run it again. And now we have 5 elements in the vector. Conveniently, the vector class supports square brackets, and we may use them just like arrays. So we can print the value of arbitrary elements by index. For example, let me print the value of element 2. Remember, the index 2 means the third element. I'll do that in line 21. We can also access elements for writing. Let me change the number at index 2. The new value will be 13. And let's print its value once again. Let's see it running. And as you can see, the element at index 2 changes from 5 to 13. Great! Now let's get some cows into a vector. I'll declare this new vector in line 26. Let me call it cattle. To enter each cow, we can use the overloaded constructor we wrote. So let me add 4 cows. Here is the constructor. And lastly, I'll print the name of some cows, but I'll do it using a different way of accessing the vector. Vectors support iterators, which are special objects that allow you to traverse containers. They work with similar semantics as pointers. In fact, pointers are a type of iterator. In line 32, let me print the name of the first cow in the vector. To access the first element in a vector, we can use the begin function, which returns an iterator to the first element. Once again, notice that since iterators work like pointers, we can use the member of pointer or arrow operator to access the getName function. Conversely, to access the last element, we can use the end function, but this one returns an iterator to the element after the last element. So we need to decrease this iterator by 1. For this, I can simply subtract 1 to the function's return value. Or I can use a special function called prev, as in previous, which guarantees going back a number of positions in the container. Let me use this to access the next to last cow. The syntax goes like this. First you type prev. The first argument is the iterator, and the second argument is the number of positions you want to go back. In our case, that's 2. And why not, let me show the second cow's name by index. Notice that in this case, I'm accessing the getName function with the member of object or dot operator, because this is not an iterator, it's an object. So let's see it working. And there's what we expected. Our cows are Betty, Libby, Trudy, and Betsy. It's time to start shaping our student record system. To this end, your task is to create 3 classes: student, course, and grade. With these classes, we'll be able to model students taking courses and getting grades. The student class must have 2 members, an integer for the student's ID and a string for the name. The course class must have an integer for the course ID, a string for the name, and an 8-bit integer for the credits. And the grade class must have an integer for the student ID, an integer for the course ID, and a char for the grade as an ASCII character. We'll only use uppercase A, B, C, D, and F for the grades, no plus or minus. For these classes, your task is to write the constructors and getter function implementations. I have provided the class definitions in records.h. You'll have to write the function implementations in records.cpp. And you don't have to write the test code from scratch. Feel free to use the code I've provided in the usual code demo file. So please take a minute to look at the source files before you start writing your implementations. This may take you about 20 minutes. When you are finished, let me show you my solution in the next video. Here's my solution. The records.cpp file starts by including the .h file. That's important because that file contains the function prototypes. I'm using the namespace std to simplify my typing of the string class. Remember that it's not a very good idea to put this line in the .h file. And next, notice that the constructors are simply assigning the arguments to the member variables. You can see the constructor for the student class in line 5 and the constructor for the course class in line 16. And the getter functions are even simpler. They just return the member variable they're supposed to return. They are all one-liners. Here you can see the constructor and getter functions for the grade class. Now let's look at the test code. Starting at line 10, I'm creating one object for each class. We have student number 1 named Hilda Jones. We have course number 7 named Physics 101 with 4 credits. And we have a grade, which is for student number 1, Hilda, at the course number 7, Physics, and she got a B. Remember, this is a single character, not a string. In the main function, I'm printing out some elements of these objects. Let's try it. As you can see, everything is shown as expected. The student is Hilda Jones, the course is Physics 101, that course has 4 credits, and Hilda got a B in Physics. Now let's get to know some control statements. These are parts of the code where execution may take different paths depending on some condition. Let's start with if-else statements. First, let me declare some variables starting at line 9. An integer named a initialized at 1023, a boolean named flag initialized as false, and a char named letter initialized as d, lowercase. Now let's go to the main function to write some conditionals. The syntax for an if statement goes like this. First we type the if keyword, then comes the condition, which always goes between parentheses. I'll compare a to 1000. If it's greater than 1000, I'll print a message on the screen. So after the conditional comes the block of code you want to execute when the condition is true. There is no then keyword. I want you to notice 2 things. First, if a block of code consists of exactly 1 line, there is no need for curly brackets. You may place them if you want, but they're not required. And second, the else part is optional. There are some cases where you only care about the case where the condition is true, like this one. Now let me show you an if-else statement. This time my condition will check if a is an even or odd number, and I want to report either case to the screen. So to do that, I can calculate the remainder of dividing a by 2. If the remainder is 1, then a is odd. If it's 0, then a is even. So I'll use the remainder operator and compare it to 0. Notice that I'm using the double equal operator, which is the comparison operator, not the assignment operator, which is single equal. But think about this. Remember that in C and C++, 0 means false, and anything other than 0 means true. So comparing something to 0 is the same as comparing it to false. If the expression results in 0, then the else part will be executed. There's no need to compare to 0. So I'll just leave the remainder expression as my condition. When this result is true, the number is odd. So let me write that. Now comes the else keyword, and the block for the false path follows. Now this trick of performing some operation without a comparison only works when you intend to compare to 0. But it may make your code difficult to understand, so feel free to compare explicitly if you prefer. Conditions may be long expressions. For example, let's report if a letter is a vowel or not. I'll do this by conditionally printing not in the middle of a sentence. The sentence will start with the letter, whichever letter we have, is, then we decide whether to print not. For this, I'll compare the letter with all 5 vowels in their lowercase and uppercase versions. So that's 10 comparisons. I'll check if the letter is not A, and not E, and not I, and so on. You may break lines as you please in C++. Then, in the positive case of the condition, we print not. And after the if statement, we finish the sentence. Finally, you may hold conditions in Boolean variables and check their values later. Let me place an if statement that uses our flag. There, let's see it working. As you can see, everything looks as expected. A is over 1000, A is odd because it's 1023, and the letter D is not a vowel. Now go ahead and change the values of the variables to see the opposite behaviors. Case statements are called switches in C and C++. A switch is a branching statement that allows your program to take one of several paths based on the value of a variable. It's like an if-else statement, but with any number of outcomes, not just 2. For this, let me show you a quick and dirty calculator. In line 9, I have declared 3 floating point variables, operand 1, operand 2, and result. And I also declared a char for the user to choose the operation to perform between those 2 operands. In the main function, I've written some code to get both operands and the operation from the user. So let's take it from there. In line 20, I'll start writing our switch statement. The syntax goes like this. Type switch, followed by the name of the variable between parentheses. We'll decide based on the operation selected by the user. Next, the code block inside the switch statement is very particular and it requires curly brackets. Inside, we list every case we want to react to. We do this with the case keyword, followed by a constant of interest and a colon. I'll start with the plus sign for addition. Notice that this is a character constant, so it's enclosed by single quotes. Now, control will be transferred to this entry point if operand is the plus sign, and it will go on until it reaches either a break statement or the switch ends. For a classic case statement behavior, you'll want to end every case block with a break statement, which terminates the execution of the code inside the switch. So, for the plus sign, I will assign the addition of the operands to result and add a break. Let me do the same for subtraction, multiplication, and division. Also, switches allow you to specify a default case for any value not specified above. I'll use addition here. That's it for the switch. Notice that line 38 is reporting the result. So let's try it. So let's multiply 3 by 7. I'll choose multiplication, and the result is 21. Go ahead and try the other operations. Now let's get to know loops. The simplest loop in C++ is the while loop. It has 2 forms, while, which evaluates a condition prior to iterating, and do while, which always runs the first iteration and evaluates the condition at the end of the loop body. Let me show you how to print all the elements of a vector with a while loop. In line 10, we have the declaration of the vector named numbers. And just like arrays, vectors can be initialized at declaration with a list. Here I wrote 5 values in ascending order. Then, in line 13, we have an iterator declaration and initialization. This iterator will be used to traverse the vector. Notice that iterators are usually defined within their classes, even generic classes. So that's what the double colon means. This iterator type belongs to the vector of integers class. I've initialized it at numbers.begin, which is an iterator pointing to the first element of the vector. I named it PTR as in pointer. Now, with a type name as complicated as this one, this is a good opportunity to use the auto type. Like this. The loop starts with the keyword while, followed by a condition to keep iterating as long as the condition is true. So I'll iterate while PTR is not equal to numbers.end, which is the element past the last element in the vector. Now the body of the loop will have a line to print the element PTR is currently pointing to, and a line to move the iterator forward by one position. I'll use the function named next for that. Now about the do-while loop, you may want to use this type of loop when you are absolutely sure it's safe to run the body of the loop the first time. In this example, I'll do the same as above, and I know that the vector has 5 elements. Also, I'll access the vector by index this time, so let me declare an integer I initialized at 0. The loop starts with the do keyword, followed by the body of the loop. The loop ends with the while keyword and the condition. This has to end with a semicolon. The loop will iterate while I is less than the number of elements in the vector. We can get that number with the size member function. Now the body is the same as the previous loop, but accessing the vector by index. We print the numbers indexed at I, and we increment I by 1. This is the postfix increment operator double plus. That's it. We expect to see the vector elements printed twice in 2 separate lines as initialized in ascending order. Yes, there we have it. 12, 25, 31, 47, and 58. For loops are typically used when you know the range to traverse in advance. The first and last iterations are normally specified in the loop statement. Well, for loops in C and C++ are extremely flexible. A for loop has a directly equivalent implementation with a while loop. In this example, I'll calculate the average of the elements in the same vector we saw in the while loop example. That's why we have a float definition for the average in line 11. So let's go to the main function. Let me start in line 14 by initializing the average to 0. Now, the for loop syntax has 3 parts separated by semicolons. First we have the initialization statement, then the condition, and lastly the increment expression. So let me type for, and the first part is the initialization of the iterating variable. And you may declare that variable in this part, so it will belong to the scope of the body of the loop. It will be an integer named I, initialized to 0. Don't forget the semicolon. Now comes the second part, the condition to iterate as in a while loop. My condition will be while I is less than the size of the vector. And the third part is the increment. It's simply I++. The body of the loop is a one-liner. I'll add the current element to the average. Now, outside the loop, let me divide the average by the size of the vector. Once again, here we have a shorthand operator for assignment and division. And then let's print the value of the average. Now let's do the same thing again, but let me show you another form of the for loop. This form was added in the C++ 11 standard. This is the range-based for loop, and as the name suggests, it works by traversing a specified range with an iterator. As you can see, I have copied the previous code, and I will simply modify lines 21 and 22. The syntax is quite simple. First, you specify a variable to traverse the container, a colon, and the name of the container. In our case, let me declare an integer, but I'll use the auto type and name it x. Then a colon and the name of the vector. You may read this as for each x in numbers. Now, be warned that using a variable of the same type as the elements in a vector or array will copy the value of each element for each iteration of the loop. So this is okay in this example where we have a vector of integers. However, if you have a vector of objects, you may want to use a reference instead. We'll see some examples of this later. So in the body of the loop, we can safely treat x as the current element. We'll do the same as in the previous loop. So we expect to see the average of the values in the vector printed twice. And here it is, 34.6. Great, let's move on. It's time for another challenge. This time your task is to calculate the grade point average, or GPA, for a student. You'll retrieve the data from a vector of grades. And you'll print the GPA on the screen. To calculate the GPA, please use this formula. The GPA for a student equals the total points awarded in all their courses divided by the total amount of credits in those courses. As a part of calculating the points, we'll use this table to convert letter grades to points. An A is worth 4 points, B means 3, C means 2, D 1, and 0 points for an F. To be clear, let's look at an example. Let's say some student named George took 3 courses: Algebra, Physics, and English. Algebra is worth 5 credits, Physics 4 credits, and English 3 credits. And he got a B in Algebra, an A in Physics, and a C in English. So to calculate George's GPA, the total points are calculated by adding the products of the grades by the credits in each course. We'll divide this by the total number of credits in the courses. So in this example, George would get a GPA of 3.08. You'll start from my solution to the previous challenge, but this time I have created 3 vectors of objects of each class. Starting at line 11, we have a students vector which is initialized with 2 students, George P. Burdell and Nancy Rhodes. I entered all IDs sequentially starting from 1. Then we have a courses vector with 4 courses. We have Algebra, Physics, English, and Economics with 5, 4, 3, and 4 credits respectively. And then we have a vector of grades, where the grades for all students are stored. The first line has the grades for student number 1, George. If you take a minute to look at these grades, you'll see that George is the same example for a GPA calculation I just showed you. Then the second line has Nancy's grades. Moving on, the main function has the code to get an ID from the user, that should be 1 or 2, and it finally prints the value of the GPA global variable. So please fill in the blank in lines 29 and 30 with your code to calculate the GPA for the selected student. Also notice that line 33 is just a placeholder that gets the name of the first student in the student's vector. So please replace that line with the correct code to get the name of the selected student in the student str string. This challenge should take you about 20 minutes, so give it a go, have fun, and watch the next video for my solution. Here's my solution. Let's start at line 29. I've declared 2 floats to hold the total points and the total credits respectively, both initialized at 0. Next, in line 30 we have a ranged for loop for all elements in the grades vector. The current element will be in the GRD reference. Notice that its type is not grade, but grade ampersand. That means that GRD is a reference to the current element. This is done to avoid copying every element to GRD as the loop progresses, because objects tend to have a lot of data in them. And making a copy is definitely not what we need right now. We just need to traverse the vector. We could also do this with a pointer. References to objects like GRD use the same syntax as the actual objects. So we may treat GRD as the current element of the grades vector in the loop. You may also use auto instead of grades here, but I'll leave it as it is. Since the grades vector contains grades for every student, I'll only consider the grades for the selected student in the ID variable. That's what the if statement is doing. Basically, I'm checking each element in the grades vector to see if it's a grade for the selected student. If it's not, we just move on to the next entry. Also notice that this if statement is the only part of the loop body, so I'm not using curly brackets. Now, remember that the grade is a letter, so we have to convert it to its number equivalent. So in line 32, I have declared a float named numGRD to hold the numeric grade for each letter. In the switch statement, you can see that I'm assigning different values to numGRD depending on the letter. A is 4, B is 3, C is 2, D is 1, and anything else is 0, including F. Now, as the comment in line 45 reads, we'll calculate the total credits and points, which we need to calculate the GPA. The first thing I do is look for the credits of GRD with a while loop in line 47. Look at the condition. First, we have an integer named j initialized at 0. So the first thing the condition checks is that j isn't equal to the size of the courses vector. I'm checking this because the next part of the condition would be unsafe if the first condition isn't met. Notice the double ampersand operator. That means logical AND, not bitwise AND. So a nice thing about logical AND and OR operations is that they perform short-circuit evaluation, so we can do what we have in this line. In the first part of the AND, check if it's safe to evaluate the second part, because if it's not, then the second part will not be evaluated. So in the second part of the condition, I check if the ID of the course at index j is the course for the grade we are currently looking at. The body of the loop is a simple increment of j. So what it does is traverse the course vector until it finds the course for the current grade. After the loop is done, j will be the index to the course we're interested in. In line 49, I am adding the credits for this course to the credits count. And in line 50, I'm adding to the points count the product of the current grade and the course's credits. After the for loop is done, points and credits contain just what we need to calculate the GPA, and that's what I did in line 52. Lastly, we're supposed to print out the name of the selected student with the student str string starting at line 54. So for this, I did pretty much the same as for the course's credits. Traverse the student's vector until I find the requested ID, and then assign that name to student str. So let's see it working. Let's look at the GPA for George, whose ID is 1. There it is. The GPA for George P. Burdell is 3.08. Go ahead and try it for Nancy. Finally, you may have noticed that there are many things that may go wrong with this code, for example, if some course ID or student ID is not found. So you may want to add these validations as an additional exercise. We have been using functions in pretty much every example up to this point. Now it's time to take a closer look at functions and their many advantages. Functions provide modularity to your code. That's why virtually every programming language supports them. Functions are procedural blocks of code that return a value. They usually receive a fixed number of arguments of specific types, but some functions use a variable number of arguments. Now, there's a distinction between the terms parameter and argument. Arguments are the variables or constants that are sent to the function when it is called. Parameters, on the other hand, are the variables in the function that take the values of their arguments. Also, functions may be global or they may be members of a class, just the same we call methods in Java and Python. Let me show you how to define both types of functions. For this, we'll start with the student record system where we left it. Now, you may have noticed that there are several things that seem out of place in this code if you look at it from an object-oriented standpoint. For example, allowing the main function to access the vectors. or getting the numeric value of each grade in the main function, or looking through a vector to retrieve data from the ID. If these things look reckless or out of place to you, you're right. It looks like these vectors belong somewhere other than the main source file. In fact, we may encapsulate most of this code in one class. So let me show you how I copied those vectors to a class named Student Records and how I have prepared the class to move that misplaced code to an appropriate location. Let's go to records.h. Then in line 43, I declared the Student Records class. It has 3 private data members, which are the same vectors we had in the main code. Then we have a private member function, getNumGrade, for converting letter grades to numbers. Notice that I'm not specifying the parameter names just yet. It turns out that the declaration informs the compiler about the return type, the function's name, and the parameter types. This is known as the function prototype. The definition, on the other hand, implements the function procedure. The names of the parameters are not required in the function declaration, but they are mandatory in the definition. Now all the public members are functions. The first 3 add elements to the vectors. That's addStudent, addCourse, and addGrade. These will replace the insertion of elements in our original code. The remaining functions are getStudentName, getCourseCredits, and getGPA, which will also replace most of our code in the main function. Did you notice that I didn't overload the constructor? It turns out that I don't need to initialize anything when I create my student records objects, so the default constructor will do. So let's look at the implementations in records.cpp. Starting at line 47, the addStudent, addCourse, and addGrade functions simply use the pushback function to add elements to their vectors. The rest of the functions aren't implemented yet, so I'll move some code from the main function into these functions and make some adaptations. Let's start with the getNumGrade function. This function receives a letter grade in a char and returns a float. In the main source file, that conversion is done with the switch statement in lines 32 through 44. So let me cut this code and leave a comment here. Get numeric grade. Now I'll paste that code as the body of the function. I'll have to change the variable checked in the switch. I'll replace it with the parameter, which is called letter. And finally, I'll return numgrd. Great. Let's move on to getStudentName. This function takes the ID of the student as a parameter and returns the name as a string. In the main code, we do this in lines 42 through 46. Let me cut and leave a comment. GetStudentName. And let me paste it as the body of the function. The parameter is called SID, so let me change that in the while loop. Also, since we are only assigning the student's name to the string at the end, we can get rid of that string variable and simply return the result of the getName function, like this. Moving on, we have the getCourseCredits function. This one is very similar to the previous one, so let's go to the main function. The code is in lines 34 through 37, but notice that the last line is doing 2 things: getting the credits and adding them to the credits variable. So I'll note this in a comment. Now let me adapt the function . Great, now we are ready to use these functions. You may have noticed that there's one function left to implement. In this function, we'll use most of the functions we have just implemented. This is the getGPA function. In the main source, this is between lines 29 and 37. So let me cut and leave a comment. Now let's adapt the code. The first change is in line 93. The ID is our parameter called SID. Then in line 94, we have the node I left to get the numeric grade from the letter grade. But notice that the numGRD variable is used in line 97, so let me place the function called there. Instead of numGRD, I'll call the getNumGrade function, passing the grade from our GRD object. Let me get rid of the comment. And now, in line 95, we have to update the credits variable. Let me uncomment this and call the getCredits function. The argument is the course ID, which is in the GRD object. Now look at line 96. This line also uses the current course's credits, so let me put this value in a variable to use it in these two lines. Remember, this is an unsigned char, and I'll name it current credits. So let me assign the function call to it, and use its value in lines 96 and 97. And now we can return the value that was previously assigned to GPA. There, we are done getting that messy code into our class. Now let's use this code in the main source file. There's still some cleanup to do. The GPA floating point variable is no longer useful to us because we'll only use it once to print its value, so I'll get rid of it. I'll also get rid of the getGPA comment. Then I'll call the GPA function instead of reading the variable up ahead. But for that, we need a student records object. Let me declare a global one in line 22. I'll call it SR. Now we can call some functions. In line 29, we have to get the student's name. So let me declare the string for it and call the getStudentName function. Lastly, let me call the GPA function that was pending in line 30. But we are not done yet. We still have those vector declarations which used to initialize our vectors in the original version of the code. Now we have the adder functions for that. So now that we need to get that data into our vectors in the SR object, this is a good chance to create a global function. Now, the compiler formally requires you to write a function declaration or prototype and a function definition. Recall that function declarations are usually written in a .h file, and the implementations in a corresponding .cpp file. You may sometimes get away with not declaring your functions and just defining them right away in the code, but this is considered a bad practice. So let's go to line 11 and declare a function that doesn't receive any parameters and doesn't return anything. I'll name it initialize. I'm declaring this function in the user source file because this function has nothing to do with the student record system classes. In fact, declaring global functions in header files is sometimes considered a bad practice. If you must do it, those functions are usually declared within a namespace. Now let me copy this prototype and go all the way down to the bottom of the file, right below the main function. And this is where I'll implement this function. I am allowed to do this because I have already declared the function, so whenever the function is used in main, the compiler will know the types to use or not. So let me move the original vector declarations to this function and adapt the code to use the add functions. So for example, to add students, I'll use the addStudent function, and the arguments will be the same as the ones we used in the constructor. Now let me do the same for the rest of the entries. The last change left to do is calling this function. I'll do that in line 17. Now we are done. Let's see if it behaves like the original version. Let's look at the GPA for George. Oh yeah, it seems to be working all right. Now I'd like to take a moment to tell you a bit more about function parameters. In many programming languages, you may pass arguments by value or by reference. C++ implements 3 variants of this. Normally, arguments are passed by value. This means that inside the function, you'll have copies of the variables sent as arguments. You can't modify the original variables. You may also pass arguments as pointers. That means that you may send the address of the variable as an argument. This will give you the power to access the variable inside the function. This may be dangerous, but it's a possibility. And you may also pass arguments as references. This is similar to passing arguments as pointers, but the limitations of references often make this the smart and safe choice. Now I'll show you a simple example for you to see the syntax of these three different ways of declaring your function parameters. I'll create three functions, one that takes arguments by value, one by pointer, and one by reference. In line 10, I have declared two integers, a initialized at 9 and b uninitialized. Then I have a series of lines to print their values. In between those lines, I'll call each of these functions just to verify that they work. So the first function will be used to assign a value to b. This function will return an integer containing the square of its argument. Let me do this in line 9. Notice that the parameter x is declared as an integer. So this is the normal way of passing arguments by value. X will receive the value of the integer that is sent to the function as an argument. This argument may be a variable or a constant. Whichever is the case, x will be assigned that value. The body of the function is quite simple, but I want you to see that there's no problem at all if I modify x. Let me assign the square of x back to x. Yes, I've lost the value of the argument because I've overridden it. However, x is an automatic variable. It will cease to exist once the function returns. Now let me return x. Once again, returning x doesn't mean that x will make it outside the scope of the function. No, its value will be returned. In the main function, let me assign the square of a to b. Now let me implement two swap functions. Both functions will interchange the values between their two arguments. In line 16, let me define the first one, receiving arguments by address, that is, as pointers. The function doesn't return anything and uses two pointers to integers as parameters, x and y. To implement the swap, I'll use a temporary integer called temp. Temp will get the value of the integer where x is pointing. Notice the indirection operator. Where x is pointing will get the value of the variable where y is pointing. And finally, where y is pointing will get temp. Now let me call that function in line 26. A and b must be passed as addresses, so I'll use the addressOf operator. Notice that technically we're still passing arguments by value because we are not passing a or b. We are passing their addresses to a couple of pointers that will receive those values, which are addresses. Okay, now let's create the remaining function, which takes arguments by reference. Let me do that in line 23. This will be an overload of the previous swap function. Remember, that means that this is another version of that function with a different parameter list. My parameters will also be called x and y, but notice the ampersand at the end of their type. That means they're references. The body of the function is very similar to the body of the function that uses pointers, but I don't need to dereference. Remember, references are aliases, so they are treated as the variables themselves. This is very interesting because it gives you access to variables outside the scope of the function. So now all we have to do is call this function. I'll do that in line 35. And we are ready to try it. So as you can see, we correctly calculated the square of 9, which is 81, and a and b are being swapped twice. It's time for another challenge. This time your task is to create a function in the Student Records class. You'll work with the code as we left it. The function must receive a student's ID as an integer, and it must print a report card on the screen. This report card must include the name of the student, the course names, the letter grades, and the GPA. Feel free to start your function with the code for the GPA function. You may even piggyback on that code, or you may choose to start from scratch. Your choice. For this challenge, I have modified the main function to have a function call in line 22. Please make sure your function matches this name. This may take you about 30 minutes, so have fun and make sure to watch the next video for my solution. Here's my solution. Starting at line 110, I created the report card function as I suggested. I simply copied the getGPA function and added lines to print some data. The first one is line 110, where I'm printing the name of the student. Then, in line 115, I'm printing the course name and grade. Notice that I needed another function to fetch the course grade. Let's look at it. Starting at line 103, as you can see, I'm doing the same sequential search as in the getCourseCredits and the getStudentName functions. Now, if you're thinking that sequential search is not the best search algorithm out there, you're right. The code could definitely do better. I'm doing this mostly because I'm using plain vectors. The standard template library comes with a variety of containers, among which you'll certainly find the most suitable for your applications. Going back to the report card function, the last change I made to the original GPA function is in line 120. That was the return line in the GPA function, but the report card function has a void return type. So I replaced that with the printing line of the GPA. Let's see it working. This time I'll request the report card for Nancy, whose ID is 2. And there it is. Nancy got an A in algebra, an A in physics, and a B in economics. That's a GPA of 3.69. Now let me show you how to read text files. For that, the standard library provides the fstream header, which I've included in line 7. This header is part of the input-output library and provides a number of classes to handle files. In line 11, we have the declaration of an ifstream object called inFile. The ifstream class is an input stream from a file, and so it works very similar to the cin object. Next, we have the declarations for a string, an integer, and a char, which will be used to store values coming from the file. In the main function, the first thing I do is open a file with the open member function of inFile. The file is called people.txt. After successfully running this function, we can use inFile to read that file we just opened. But this function may run into an error, so we have to check if everything went well. That's why in line 18, I'm using the fail function to check if the open function failed. If it did, I print a message on the screen. And if it was successful, we have the else part in line 20. Now, there are many ways to run sanity checks on your files. But for now, I will simply assume that the file has the exact format I expect. For example, we may assume that some other program has produced this file, so if the file is found, it must have the correct format. Speaking of which, let me show you the format of my file. The file has a series of entries with a name, an age, which is supposed to be an integer, and a letter, which is the first initial of the name. For our example, we'll extract the names as strings, the ages as strings and convert them to integers, and lastly the initials as strings and convert them to characters. We'll do that as long as we find entries in the file. So back to the code, the while loop in line 21 will iterate as long as the end of file is not reached. That's what the EOF function returns. Then we have the getLine function in line 22. This function is defined in the string header. It takes one line of text from the stream in the first argument and replaces the contents of the string in the second argument with the acquired text. You can use this function with cin as your input stream if you want to read complete lines of text instead of separate words from the terminal. So the getLine function is taking one line of text from the input file and writing it to str. Next, I'm printing that line on the screen. Once the while loop is done, I close the file. It's important to close the files you'll no longer need. This code should print the complete file on the screen. Let's see it. There you have it. 4 entries of names, ages, and initials. Now, once again, assuming the file has the exact intended format, let me extract the names as strings, the ages as integers, and the initials as single characters. So let me replace the end line with a comma. Now I'll call the getLine function again. And to convert the incoming string to an integer, we can use the s2i function in the string header. It simply returns the integer represented by the string. Now I'll print that integer. And lastly, I'll call the getLine function once more. And since I know the string will contain one letter, I can get that character by indexing the string because the square bracket operator is supported by the string class. And let me print that character and break the line. Let's see it running. And everything seems to have been fetched okay. For this example, I'm only printing the elements in the file, but as you were able to see, converting data from strings can be very easy. Here's a quick example to show you how to write into a text file. It looks very much like the file reading example, and it's actually a bit simpler. In line 11, we have a declaration for an OFStream object named outFile. Then we have 2 floats of arbitrary values, a and b. In the main function, we have the same logic as before. First, we open the file in line 15, and the open function may take a second argument to specify the mode of the file usage. By default, it will allow us to write into the file, and if the file already exists, it will replace its contents. There is an append mode to continue writing into the file starting after its last character. Failure may occur if the file is already open for writing by some other object or program, so I report that in line 17. And starting at line 19, I'm using the outFile object to write into the file. The good news is that we can use the left-bound insertion operator just the way we've been using it with cout. So I'm writing the value of A in one line, then the value of B in another line, and then their addition and product. So notice that the insertion operator takes care of converting those floats to strings before writing into the file. Finally, I close the file and I report that it was written successfully in line 24. So let's see it running. And here we just get the message, file written successfully. So let me open the file. And as you can see, the file has the expected contents indeed. It's time for our final challenge. This time your task is to upgrade your report card application to work with text files. You'll have to retrieve all student, course, and grade data from text files. And then create a report card for all students in a text file named report.txt. For the input files, please use the provided students.txt, courses.txt, and grades.txt. These files have the same format I used in the file reading exercise, with one value per line and ending at the last character. For example, the students file has a series of ID name pairs, with the ID in one line and the name in the next line. The file ends in the last character of the last name. There is no empty line at the end. This is crucial because this is how you'll know that you're done reading the file. These files come with the data we've been working with for George and Nancy. Take a minute to look at these files to make sure you understand how they're organized. After doing that, add at least one more entry to each file. That's one additional student, one additional course, and at least one additional grade. Do that manually. This should take you about 30 minutes. As usual, watch the next video for my solution when you are done, or if you get stuck. Here's my solution. First, I created an ifstream and an ofstream objects named inFile and outFile as before. Then I modified the main code to use two new functions. The first one is in line 21, where I initialize the student records object from the input file, and the second one is in line 22, where I call a member function of SR called reportFile. You can see the prototype for the initialize function in line 13. Notice that it's an overload that receives an input file stream reference. I left the original function defined anyway, so let's scroll down to look at the initialize function implementation. At this point, I think you'll be able to tell how I copied and pasted the file reading example 3 times here and adapted that code to read the student's file first, starting at line 33, then reading the courses file starting at line 49, and then the same thing for the grades file in line 67. After reading each file, I'm reporting to the screen how many entries I found. Now, for the report file member function, let's go to records.cpp. But first, since the code for the report cards was going to be almost the same as the report card function, I decided to modify that function a bit to receive a second argument as reference. It's an output stream object. I named the parameter stream, and I replaced the occurrences of cout with stream. You can see this highlighted in lines 113, 116, and 121. So now this function works for either cout, that's the screen, or a file for writing. So the new form of this function to print a report card to the screen will have the student ID and then cout as arguments. Now for the report file function, most of the work is already done for us. It starts at line 124. The function receives an output file stream as reference, and it uses it in line 126, where it opens report.txt as usual. Now the work starts at line 130 after the error checking. First I place a horizontal delimiter, and then we have a ranged for loop that gets every element in the student's vector in a reference named st. So in line 132, I get the student ID in the SID variable, and then I call the report card function operating on outFile. So it will print the same report card, but in our report.txt file. After each report card, we have a new horizontal delimiter in line 134. If everything goes well, line 137 reports success. Let's go back to the main function. As you can see in lines 21 and 22, I'm calling the file-based functions, but the comments at the right show the previous version of the initialize function, which still works, and the new version of the report card function in case you want to use them. So let's see it working. Here you can see that the program found 2 students, 4 courses, and 6 grades, and finally it created report.txt successfully. So let's look at that text file. And here we have both report cards. Now go ahead and try it with your extra entries. That's it! You made it to the end of the course. Give yourself a pat on the back. Of course, there's a long road ahead to master this amazing programming language. As next steps, I'd like to suggest learning about the C++ standard template library. You may want to consider my LinkedIn Learning course about it. You should also learn about the best programming practices for C++. Some of these practices come with different coding styles, and you'll find recommendations on how to comment your code, how to use namespaces, what to include and avoid in header files, and so on. You should also learn more object-oriented programming features of C++, such as inheritance and polymorphism. And lastly, you should learn about modern frameworks to get your code into useful everyday applications like web services or mobile device apps.